So they really gonna go. Tell her to take.
Okay. No, please don't be Edward. Put it in the thing and sign your name on it.
Okay.
You know what? I'm just
What else would I do?
Well, Edward decides to not put it in an envelope, not sign it, not finish it, and give it back to me. Oh, yes.
Alright, let's start with the calculator questions. Are there any questions on those? Did my explanations make sense?
Honestly, I didn't look at explanations because I got all the answers. Can you do the particle moving along a straight line?
Is that like the last one?
The last one on the first paper. Yeah.
Oh, okay.
So I have
Okay.
so this is
So on this one, okay, a particle moves along a straight line with a velocity given by this, right? 7 minus 1.01 to the negative t squared power. And we want to figure out the acceleration when t equals 3. So on this one, acceleration is the derivative of velocity, right? So this question is just asking me to take the derivative of that velocity function and plug in 3. We can do that all in one step on the calculator. So let me pull up the calculator here. She had to prove it to you. Alright, so got algebra. Alright, so from the home screen I can do math 8, and then I can just type this in. I want the derivative of this function. So d over dx of 7 minus 1.01 to the negative t squared, so negative x squared power. And I want to evaluate this at x equals 3. So the calculator tells me the slope of this function at 3 is 0.055. Okay. So that's all we had to do for this one. Right? We just needed the slope at a certain point. And this was a one-step problem, actually. You okay with that one? Other questions? So it is.
Where did it go?
No other questions?
Thank you.
Thank you. All right, if there are no other questions, then today we are going to start integrals.
What?
No.
Get
Sounds like something I do
pumped.
not want.
All right, so this is kind of starting the second half of the year.
We're already on the second.
Mr.
Yes.
Peck, you should collect this paper as a grade.
Or just get the compilation because we all did it.
Yeah, we all did it. You should put it in as a mastery grade.
I'm not putting it in as a mastery grade. I sent you the answers.
Oh, I didn't look at them, so technically, I can solve by myself.
I will. I mean, everybody worked on it well yesterday, so I'll give you a completion grade for it.
I didn't do my test.
I don't know if this will make up for test correction.
I did 2 of them and then I realized
I can never correct all of my corrections.
Why not?
Like, I feel like I understand what I did wrong, but a lot of the time I cannot do it. I don't remember.
Then ask me questions.
I do. It makes a lot of sense.
I feel like
I am dumb. So,
No, but you didn't ask me any questions.
I did. Well, Andy tried to help as well.
Maybe
I figured it out, but a lot of the time I'm like, I can't
You can't have the very
Alright,
I love it, okay?
we are going to start with a few pretty basic questions. Okay? These are like 6th grade math questions. Okay, so let's take a second and try to figure these out. I do not have a guided note sheet, okay? So you're taking your own notes today. If a train travels 80 miles an hour for 4 hours, I hope you can figure out how far it went.
300.
There you go.
Oh, you just do 800. I'm sort it for me. You could not figure it out. What was it? They were saying, how's your makeup look for you?
Why is that? Why is that?
Yeah, they are gonna figure it out. What? Hey, shut up. Try to learn math. You're not trying to do anything. Oh, I have my notebook. I can't talk. Thank you.
Alright, so let's take a couple of minutes here and try to figure out these 4 questions.
I was always bad at these types of questions.
I didn't pay attention to Mr. Molly's class.
Today's going to be a struggle if you can't figure out questions like this.
Goes all the way to the top of everything that to an edge of the non-traditional. That's the most random people. No.
You could just clear the memory. That would erase everything.
How do I do that? Because look, they were all the way here. And I had to go down to like that.
So, second plus
Let's see how many I can get wrong here.
Do we have answers? Yes.
Woo!
3 degrees.
Well, it went down.
Yeah. Alright. So, did we get these answers?
I can math.
Okay. So, let's look at these from a calculus perspective now. Okay. This first question, train travels 80 miles an hour for 4 hours. How far does it travel? I can graph this, right? I can say that it was moving at a constant velocity of 80 miles an hour. So if I graph that, I'm graphing this line at 80, right? It's moving at a constant velocity. So I'm graphing the velocity and saying that this is at 80. Well, if I want to figure out how far it traveled after 4 hours, okay, I can say that the 4-hour mark is here on my time axis. What I can do is find this area, okay, the area under the curve. This is just a rectangle, right? That's 4 by 80. So 4 times 80 gets me that it traveled 320 miles. Similarly, for number 2, if I graph this, okay, I'm graphing acceleration this time. I'm saying the acceleration was a constant 5 miles per feet per second, not miles per hour, feet per second squared. So my acceleration's here, and I want to figure out, well, after 10 seconds, what's the velocity? Same idea. I'm finding the area of this rectangle. Okay. 5 times 10. Now what we're doing here, right, is actually called an integral. And we'll get into all that notation here later. Okay? But if I'm given a velocity function and I find the area under the curve, what I've found is position. I'm going backwards. I'm going one function up. So if we remember, velocity is the derivative of position, acceleration is the derivative of velocity. So if I'm given a velocity curve and I find area under that curve for a certain time, I have found its change in position. Similarly, if I have an acceleration curve and I find the area under that curve for a specified amount of time, I have found its change in velocity. All right. Same idea for number 3. Right. A pump working at 100 gallons per minute pumps for 2 hours. Okay, so if we want to keep our units the same, this would be 120 minutes. Right? So I'm creating a graph where this rate is 100, and I want to see what happens after 120 minutes. After 120 minutes, okay, 100 times 120, if I take the area of this rectangle, I get that 12,000 gallons have been pumped. For the 4th one, right, this one, we're saying that we drop 1 degree per hour for 12 hours. Right? So I've gone down 12 degrees, and then I go up 1.5 degrees for 6 hours. So I would be adding 1.5 times 6, which is 9. Negative 12 plus 9 gets me a net change of 3 degrees, going down 3 degrees. Okay, so we'll take a look at how to model something like that on a graph here in a second. Okay, but the biggest idea, okay, and this is basically the idea for the rest of the year, okay, finding area under a curve. In these problems, to model that, it was really straightforward. Our function that we cared about was constant. Okay, it was just a horizontal line. So finding the area under the curve was just finding a rectangle, okay, or finding the area of a rectangle. Yeah, let's make up this one here. So let's say that we are given a velocity curve of t plus 1. Right? And I want to figure out where the particle is at t equals 3. Right? This function, t plus 1, models the velocity. I'm asked about position. I want to find where the particle is. To find position, I want to find the area under this curve from 0 to 3. So if I graph this, right, this is just a line with a slope of 1 and a y-intercept of 1. Right, so it's going to do something like this. Well, it's saying all I care about is things greater than 0. And I want to figure out what happens at 3. So I want to find the area under this curve. That's going to tell me the position. Okay, area under a velocity curve tells me the position. How would I figure out the area of something like this? Yeah.
I would divide it up area like the rectangle.
Yeah, that would work. Okay, finding the area of this entire rectangle here and then getting rid of this. So this,
That's not a triangle.
what is this shape?
It's not exactly.
Quadrilateral. It's a square. Or quadratic.
Technically, it would be.
It's linear.
The line is a linear function, but what is the area of the shape underneath of it that we've created?
Is that a right or wrong?
Neither. Still haven't heard the right answer.
Rectangle?
It's not a
It's
rectangle.
No, it's not.
Trapezoid.
Is it?
It's a trapezoid.
What? It has 4 sides.
Oh,
Oh wait. Yeah.
Okay,
Trapezoid has 4 sides.
I have a question that's not related to math. Why is there a pencil and a
Right here.
in here?
In your water.
That's dino.
Dino? Why is there stuff in his water bottle?
She wants to see if the ink will come out. And he never drinks that water ever. It's been sitting there since probably day 1.
Well, since we got those water bottles.
Since we got this one. You have pens in there?
Dino put them in.
Sam put the pencil in.
That's true, yeah. Sam put the pencil in there.
Yeah, you're lucky.
You changed.
Real fast.
Okay, continue.
Alright, so back to the trapezoid. Okay? So first of all, what is a trapezoid? Since we don't seem to know our shapes.
We haven't used them in a while.
Okay, I say instead of reviewing, you make a collage of all the videos of the dumb stuff. A collage.
Please don't post this one on
Wait, I'm trying to think. Like,
Please
what
don't.
I don't know.
Okay. It has 4 sides.
A trapezoid has 4 sides. That's a good start.
It has one.
I see my trapezoid now.
Something like that. Over something.
2 sides are parallel.
What happened?
So yes, that's the answer to my question.
I didn't know you asked.
So I asked, what is the definition of a trapezoid? Okay. So a trapezoid is a quadrilateral that has exactly 1 pair of parallel sides. Okay? In this shape, these sides are parallel. Okay? These sides are not. Okay? So this is a trapezoid. Then the area of a trapezoid, which is what we're ultimately trying to find here. What's the area of a trapezoid?
Base height plus 1/2. It's something like that. It has base. Something base 1 plus base 2 times 1/2.
That's part of it.
Go share it.
Or what are we missing? Times the height.
I would like it.
Okay. The area of a trapezoid is just the average of the bases times the height. Okay. Another way to write this is just the height times base 1 plus base 2 over 2. Right? So it's the height times the average of the bases.
Okay.
Alright, yeah, so throughout the next couple of lessons, we will definitely be finding areas of trapezoids. So might be a good thing to jot down here. So how do I find the area of this trapezoid?
Well,
I don't know all of the information I need. How do I find it? So in this sense, we already have the derivative.
take it one more time.
T plus 1 is my derivative function. That's the velocity. So that's like the first derivative of position. So we're kind of thinking about going backwards now. I don't want to take derivatives anymore. I'm going backwards. We'll learn how to do this in terms of functions here soon, but I want to start thinking about taking antiderivatives. I'm going backwards now. All right? So what that means in terms of a graph is finding the area under a curve. Okay, so we're not taking a derivative. In this case, I'm just doing a little bit of geometry, right? I just want to find the area of this shape, but I don't have all the dimensions that I need right now.
Fill them in with X's.
Well, no, we can find them fairly easily.
Well, the base would be 3, right?
Well,
No, it's the side. The bases
Yeah,
are
it's
the
a
side.
side.
yeah, these are the bases. So this would be the height.
Well,
Right.
that one's 1.
How'd you get that?
Because the 1
y,
plus
yeah,
t.
y intersect.
So essentially what you did was you plugged in 0, right? Plugged in 0 and got that this y value was 1. So then we'll plug in 3 to get this y value.
Which is 4.
And we'll get that this y value is 4.
Okay.
Okay. So now we have all of the information we need, right? I have that my bases are 1, 4, and my height is 3. So the area of this trapezoid would be 3 times 1 plus 4 over 2.
I feel like I'm back in geometry.
And I
So,
did not do well in
This
I did
side
really
here,
well.
to get this height, all I did was plug in 3 into my function. So 3 plus 1
It's 4.
is 4 to
So
get the
is-
y value.
Isn't the height 4? Not 3?
No, these are the bases, right? The two parallel sides are the bases.
Oh.
The distance between the bases is the height.
Okay.
Okay? So we end up with 15 over 2. So to answer the question, okay, that tells me the change in position. The particle has moved 15 over 2, or 7.5 spaces, over this time period. So at t equals 3, the particle is at a position of 15 halves, or 7.5. We okay so far? Alright, so, and I mean, like I said, this is basically the idea for the rest of the year. So we will really be working with this idea of area under a curve. What? That is a lot of words. We're actually going to kind of skip this for now and go to this. All right, so the functions we've looked at so far were pretty easy to find the areas of just using geometry. Right? We found areas of rectangles, areas of trapezoids. But what if we want to find areas under not so nice curves? Right? Like x squared, for example. I can't just draw some nice shape underneath of the x squared curve. I can't just draw a triangle or a trapezoid or something like that underneath. So what we are going to do is approximate the area under curves. Okay? We are going to use rectangles first to do this approximation. Okay? And we're going to do this 3 different ways. Okay? We're going to use LRAM, MRAM, and RRAM. Okay? The RAM stands for Riemann
We have to know what it means.
Yes, because sometimes questions will just say, find the Riemann approximation. Okay, so RAM stands for Riemann approximation method. Okay, then the L, M, and R just stand for left, middle, and right. So if I take this is just the graph of x squared 3 different times. This first one is an example of left Riemann approximation method. All right, so I'm just finding rectangles under the curve to approximate this area. Okay, now, I mean, we can kind of see here that this isn't going to be a great estimate, and I'm missing big chunks of area here. Okay, here this one looks like it's a little bit better. Right? There's a little bit of over, a little bit of underestimate, but then this one again looks like maybe not such a great estimate. There's a lot of overestimation in this one for the area. All right. So, I mean, if we think about, we can make these approximations a lot better by using a lot fewer rectangles, making the rectangles a lot smaller. But that gets kind of tedious then in the calculations. So most of the time on the AP test, if they ask you to do a Riemann approximation, they don't have you do a ton of intervals. Okay, it might be like, make 4 rectangles underneath of the curve to approximate the area. In this case, okay, we're going to do all 3 of these examples. Okay, and what they have done here is split this region up using 6 sub-intervals. Okay, you'll see questions worded like that. Right? it'll tell you how many rectangles to use. Alright, so we're going to approximate the area under the graph of x squared from x equals 0 to x equals 3 using 6 subintervals, or using 6 rectangles. So if I want to do that, okay, if I want to approximate this area using 6 rectangles, the first thing I need to do is figure out where these rectangles are. So I need to take this region from 0 to 3 and split this up into 6 pieces. How would I do that? Yeah. That's what we're going to do. Right? If I divide 3 by 6, I get that I'm going to have each of these will have a length of 0.5, right? So 0.5, 1, 1.5, 2, 2.5. Okay, so this gives me 6 subintervals in between 0 and 3. So now, this first approximation method, the left Riemann approximation method, this means when I draw my rectangles, the height is determined by the left endpoint hitting the curve. Okay? So what that means is my first rectangle is going to be this rectangle in between 0 and 0.5. Right? When I draw this rectangle, I'm going to take its height by plugging in the left endpoint, the left point into the curve. Okay, so the height of this rectangle I will get by plugging 0 into my function. So what is the height of this first rectangle? 0, right? 0 squared is 0. So this height is 0. My next rectangle that's in between 0.5 and 1, I'm going to get its height by plugging in 0.5, the point on the left. So if I plug in 0.5, what do I get? 1/4, right, or 0.25. Right? I'm just going to keep doing that for all 6 of my rectangles to get their heights. Okay, so if my next rectangle is in between 1 and 1.5, its height I will get by plugging in 1. So 1 squared gets me a height of 1. Just keep going. Plug in 1.5. So what's 1.5 squared? 2.25. Next, plug in 2 squared. So I get this rectangle has a height of 4. And my final rectangle, its height will be determined by the y value at 2.5. So 2.5 squared is 6.25. So now to approximate the area under this curve, I want to add up the areas of all 6 of these rectangles. What would the area of this first rectangle be? Yeah, 0.5 times 0. Right? So the area is 0. How about the second one? Yeah, so that my height is still, or the width, I guess, however you want to look at it. This dimension of the rectangle is 0.5, and its height is 0.25. So 0.5 times, I guess I can write that out for now. 0.5 plus 0.25, which would be 0.125. Then my second, or I guess my third rectangle. Yep, that should be multiplication. Thank you. My next rectangle, again, this dimension is 0.5 times a height of 1. 0.5 times 1 would just be 0.5. My next one, again, this dimension is 0.5 times 2.25. Which would be 1.125. Then my next one, this is, again, this dimension is 0.5 times 4, which is 2. And then my final rectangle, 0.5 times 6.25. That would get me 3.125. So adding all of that up, 0 plus 0.125 plus 0.5 plus 1.125 plus 2 plus 3.125, what do we get? 11.375? That seems a little high. 6.875? That sounds a little bit. That would do it. Alright, so this estimate here, using our left Riemann approximation method, is 6.875. Okay, that's our estimate for the area under the curve. But we can very clearly see that that's going to be an underestimate. Right? I'm missing fairly big chunks of area here. Right? So let's do the right Riemann approximation next. So this is my R ramp, and here, the heights of the rectangles are determined by the right endpoint. Okay. We already calculated most of these heights, right? So I don't really have to do that again. So I'll come over here, and I'll redraw this. So we're still going these same subintervals. Right? From 0 to 3, we're splitting it up into 6 pieces. But now this time, if I'm using the right Riemann approximation method, the height of this first rectangle is going to be determined by the y value of the right endpoint. So the height of this first rectangle will be 0.5 squared, which will be 0.25. The height of my second rectangle will be 1 squared, which is 1. The height of my third one, 1.5 squared. Height of the next one, 2 squared. Height of this one, 2.5 squared. And then the height of my final one is 3 squared, which is 9. Right, so similar process. Okay? We actually already found a lot of these pieces as well. Right? The area of this rectangle, 0.5 times 0.25, will be 0.125. And the area of this rectangle, 0.5 times 1, will be 0.5. And the rest will continue to be the same, right? This will be 1.125, this will be 2, this will be 3.125. Plus 2 plus 3.125 plus
No.
0.5 times 9. Okay. So that would be 4.5. So if I add those 6 areas together, what do I get for my estimate for my right Riemann approximation? 11 point something.
No, not 11. Like, what am I talking about? I totally different. Hello, I am kind of yes. This is why I gave up on it.
11.375.
Oh, I'm like,
Hey, that's what I got.
I did something right. Now we do the middle one now.
Now let's do the middle. So any questions so far? Pause 1 second. Okay.
This one.
Wait, hold on. What did you multiply the R and the 0.25?
So I didn't write out what we actually multiplied. So this first rectangle was 0.5 times 0.25.
You don't have to write it out.
So you multiply that by the number you squared.
Yeah. So the dimensions of the rectangle. So with the 0.5, height of 0.25. With the 0.5, height of 1. Okay. So we're just using a bunch of rectangles to approximate the areas under these curves. Okay. Any other questions so far? All right. So let's do MRAM then. So MRAM, pretty similar. Okay, I'm still splitting this up the same way. If I want to go from 0 to 3 using 6 subintervals, so I'm splitting this up 0.5, 1, 1.5, 2, 2.5. So these are my 6 rectangles. But now, the heights of each rectangles, or of each of the rectangles, are going to be determined by the midpoint. So my first rectangle goes from 0 to 0.5. To figure out its height, I am going to plug in the point halfway in between those into my function. So I'm going to plug in 0.25 into x squared. So what is 0.25 squared?
2, 6.
So I'm plugging in the midpoint. I'm plugging in 0.25. Okay. Then for my next rectangle, I'm going to plug in the midpoint. I'm going to plug in 0.75 into my function to get the height of this rectangle. So 0.75 squared.
0.56.
Okay. Then for the next rectangle, to get the height, I'm plugging in the midpoint, which would be 1.25.
What? 1.56.
6.
2, 5.
Then we just keep going. So plugging in the midpoints. So 1.75. Then writing is too big here. The next one, 2.25. 5.0625. And finally, there's my rectangle. My midpoint here would be 2.75. So if I plug 2.75 in, 7.5625.
That is such a long.
It's a rectangle.
I feel the rectangle is slouching. The leaning tower of
I really thought you were just.
She's got all those memorized. So it's the same process now. We want to find the areas of all 6 of these rectangles. So the width is still 0.5. Right? I went from 0 to 0.5, so it's going to be 0.5 times 0.0625 for my first one.
I'm guessing you don't want these rounded.
Nah, give me the whole thing.
You want it?
Sure.
0.0312.
The next one is 0.5 times 0.5625.
2.812.
Okay, then the next one is 0.5 times 1.5625.
0.78125. I'm seeing a pattern.
What's pattern? They all end in 125?
Yup.
So then 0.5 times 3.0625.
It has yet to reach that pattern. 2.5212. Wait, except one. Sorry, that's the next one.
Yeah, this
1.521.
Alright, so I mean this is a little bit of tedious calculation, right? Adding up all these areas of rectangles.
Now
This is my favorite thing you've done so
now this one is 2.531.
Final one, 0.5 times 7.5625.
far. Oh, it doesn't end.
Yes, it does.
Oh, wait, no.
It's 3.78125. And my pin just kind of disappeared underneath the couch.
So, adding all of these areas up, we can get our approximation for our M random. So what do we get if I add all those together?
Oh. Ah. $8.9275.
So, generally, our best estimate will come from a midpoint approximation. However, and we're going to spend more time on these with tables, okay, which we'll start looking at tomorrow. Okay, we can't do a midpoint approximation if we're just given tables, and I'll explain all of this tomorrow. For tonight, though, okay, I want you guys to practice a few of these on Math Excel. Okay, we haven't had a Math Excel in a while. So there is a Math Excel assignment up. Right? What's that? Need help?
I'll figure it out.
Okay. Alright, so any questions on approximating area under curves with rectangles?
There has to be a faster way.
There is. Yes. Bingo.
Anything more?
How many people are going to be what?
So, those of you that aren't here tomorrow, make sure you watch the video.